What a great way to start this evening. Good evening, everyone. I'm Juanita Todd, and I'm the Pro-Vice-Chancellor for the College of Engineering, Science and Environment, and I'm really pleased to welcome you here this evening. I begin by acknowledging the traditional custodians of the land on which we gather here today, the Awabakal and the Worimi people, and pay respect to elders past and present, and I extend that respect to all Aboriginal and Torres Strait Islanders that might be here with us this evening. In reflection of National Science Week, I'd like to also recognise that the Aboriginal and Torres Strait Islander peoples are Australia's first scientists, engineers and innovators. And from astronomy to agriculture to ecology and medicine, Indigenous knowledges continue to shape and enrich our understanding of the world. As a university for our region, we know how important it is, our role in educating future scientists, engineers, mathematicians and environmental scientists for our region's future workforce. Our work as the region's university is only possible with the contributions of many people like those of you here tonight, so we thank you. We're delighted to have you with us for this Looking Ahead lecture. This is a series that's one of our favourite events to host, and today's edition is particularly special because we're kicking off National Science Week today. We have a fantastic keynote speaker, followed by a great chance to ask your curious, quirky and compelling questions. That's curious, quirky and compelling for this evening. And you can ask us questions about anything, but particularly the night sky, space and wonders of the universe. To get us started, please let me introduce our special guest tonight, Professor Lisa-Harvey Smith. So Professor Lisa-Harvey Smith is an astrophysicist, science communicator, and was presenter on ABC's hit television show Stargazing Live. She's published more than 50 papers on the birth, and death of stars and supermassive black holes. She's served as Australia's Women in STEM Ambassador from 2018 through to 2024 and played a leading role in the design and operation of the world's leading astronomical observatories at the CSIRO. Lisa has won the CSIRO Chairman's Medal and the Australian Museum Eureka Prize, and her award-winning science books are loved by children around the world. It is my pleasure to welcome to the stage Professor Lisa-Harvey Smith.
Thank you. Good evening, everyone. How are you? We good? Happy Science Week? Now, who saw my talk maybe 6 or 7 years ago in Newcastle about galaxies colliding? Has anyone been to that one? Yeah, got a super fan. I love it. Well, I'm not going to talk about galaxies colliding tonight. I'm so sorry, but I do want to tell you about the entire future of the universe. And I also want us to think together about what life might look like in the universe. Not just us, but out there in this infinite universe. So together, I want us to look ahead. And that was the theme I was asked by the University of Newcastle to talk about, this wonderful lecture series. And I'm really glad to be invited here. I love coming to Newcastle. And it's much happier than last time when I ran the marathon, which is a horrendous experience, as you can imagine. So what does our future hold? Are we alone? These are the questions we want to talk about tonight. And they're pretty exciting ones. Now, put your hand up if you're 16 or younger. Great, okay. Well, in my day, when I was 16, we didn't have mobile phones, we didn't have selfies. We only had clunky old cameras, like this wonderful professional photographer is using now, but they weren't as jazzy as those. They weren't digital. They were actually really old, and they had film in them. We all remember them, don't we, older people, right? But you had these clunky cameras. And as a kid, I lived in a village near nowhere, in the middle of nowhere actually, in England, and it was a very small place, and there was absolutely nothing to do, day or night really, so it was a nice place in the middle of nowhere, but at night, the only thing you could do really, the only wholesome activity, was to look at the stars. And I find myself very grateful to have lived in a beautiful place where you can actually see the stars. Now, I think Newcastle is a bit like that, isn't it? A wonderful community, not a small community, but in this region, you have dark skies. You can just drive up to the sand dunes, or you can go just south of here or out into the bush and just see a beautiful vista of stars. So when I was 16, I was already getting excited about astronomy just from doing it, just from looking up. And back to the photograph, I was cultivating my hobby in astronomy, and along came this beautiful visitor from the outer reaches of the solar system. It was Comet Hyakutake. So some of you might have seen a comet, maybe Halley's Comet, or one of the great comets of the 90s. You've had some fantastic ones in the southern hemisphere, but we've had them in the northern hemisphere too. And this one in 1996 was absolutely beautiful, and you could see it for weeks on end with the naked eye. So I got my old clunky camera, and I put it on a tripod, and I had this long thing. I screwed it into the top of the camera. It was made of metal, and I had to hold the other end and click it, and that was how you took a selfie in those days. I had to hold really, really still for about 30 seconds, and there we go. There it is. So a beautiful memory, and something that really spurred me on to want to be an astronomer professionally. So I did all the studies. I studied physics, mathematics, chemistry, and all those subjects were really interesting to me. They're not easy subjects necessarily, but it's worth persevering in those subjects because, you know, it gives you this kind of ability to adapt your knowledge to whatever situation comes along. So I think young people in the room, those types of subjects where you learn fundamental skills, maybe that might be English or other languages, maybe it might be communication, but those mathematical and physical skills are very interesting and important too. I went to do my degree in astrophysics in the University of Newcastle, not this one. There's this evil twin over in the UK. And I did my PhD at this wonderful observatory in the UK called Jodrell Bank Observatory. And it's near Manchester. And of course, it's 60 years old now. It was actually the telescope that the West, in the old parlance, first discovered that Russia had sent a satellite up into space in 1957, Sputnik. So we actually verified they weren't lying by pointing this telescope up at that. It was mostly used for radio astronomy, and it's still working now. But if you read the news recently about this telescope, it just needs a few $1 million of funding, but unfortunately the UK government has threatened to close it. So it just goes to show that we need to keep fighting for science, because the discoveries that this telescope's made over the years have been many and very exciting. So, why doesn't it look like a telescope? Is that what you're thinking? Looks like you're going to watch TV with it. So this is a radio telescope. So what it is a big dish made of metal, and stars and galaxies give off not just light and heat, but they actually give off radio waves as well. Radio waves are the invisible waves that we use in mobile phone communication. They're the reason this microphone is working. It's beaming signals to the computer, to the sound systems. So they're invisible waves that are naturally given off in space. The waves come down to the ground. Most of them miss the telescope, but some of them hit it. The ones that hit it bounce into the middle. Now, in the middle, there's an antenna right here. So clever radio engineers make this antenna, and it detects how strong the waves are from each direction. And we sort this through computers, and it enables us to make pictures of invisible things in space, sometimes very far away objects, or very exciting objects that we can't see otherwise. So the objects I was studying when I was working there were clouds of gas like this. This is called a nebula. A nebula just means cloud in Latin. So scientists use Latin to sound fancy, but there's no need. So this is just one example of millions of clouds or nebulae out there. This one, just like the ones I studied, is forming stars inside. So these are clouds of gas that originated from the Big Bang and just floating around in space, just waiting. They have potential to be stars. And gravity pulls together clumps of this material because gravity pulls things together. That's what it does. And inside the clouds is very, very dark and obscured. But with our radio telescopes, we can see inside. So when you zoom in with a radio telescope, you'll see thousands of stars inside this dark, dusty gas. And inside that, gravity's pulling together different stars, both huge, giant, massive stars and normal stars like our sun. So this process is happening all throughout the universe. It's really, really fascinating. So that's what I studied for my PhD, these really exciting star formation, how stars are born. And I also studied how stars die. Did you know stars have lives like we do? They have a birth process, they evolve, they change, they get older and slow down a bit. Sometimes they speed up a bit as they get older. And they also die, just like we do. So this is a picture of a star that died 1,020 years ago, exactly. How do we know? This is a supernova remnant. And in the year 1006, so 1006 AD, people all around the world were just getting on with their business, going around, doing their farming, doing whatever else they were doing. And one night, one day, suddenly there was this bright star in the sky that wasn't there before. It wasn't just bright, it was the brightest object, apart from the sun, we've ever seen in the night sky. It was 14 times brighter than Venus. And you might have seen Venus recently in the evenings, a really bright object in the sky. It looks like a UFO, but it doesn't move. So this is a real picture from a radio telescope of what that object looks like now. But 1,020 years ago, this object just looked like a bright star in the night sky. And over weeks and months, it faded and faded and faded. When it exploded, this star, it was so bright that you could see it during the day. Can you imagine how terrifying that would be? When you had no way of knowing what it was. So supernovae and things like this used to be called demon stars. There used to be a lot of religion about them. People were actually human sacrificed. Like, it was quite serious. People believed that monarchs and leaders, kings and queens, needed to be protected from these events. So it was incredible for these people back then. But now we know it was just a star exploding, and this happens all the time. So it's really interesting that now we can keep following this object as it expands into space, and we can see what's happening. We can measure the temperature changing in the gas. We can measure the chemicals in the gas using physics and chemistry. So it's a really fascinating field. So we do this using radio telescopes. So they're different from optical telescopes, but this is the kind of field I've been in throughout my career. And Australia's really, really good at radio telescopes. Actually, we had one of the first in the world. We're the biggest in the world, which was in a field near Hobart Airport, way back when. And they were invented around the 1930s, but around the 30s, 40s, and 50s, they were developed during World War II, some in Sydney when they were trying to find enemy aircraft and ships, and they were looking for radar signals, and they pointed their instruments out to the sea, and they heard all this interesting fuzzy noises and discovered that you could actually see distant galaxies and pulsy stars and things like that. So really interesting. So I've worked all around the world in my career. I've worked in radio telescopes in the UK, in Europe, right around the world, from China to Australia. And actually in Australia I was part of a big project to build the world's biggest telescope called the Square Kilometre Array that CSIRO was leading. And this is the Australian Square Kilometre Array Pathfinder, which is 36 dishes in Western Australia, which is a very radio quiet area there aren't any TV aerials or big computer systems or anything that creates radio interference. So it's been really interesting to work in a career where I work with a lot of engineers as well, and regional communities, and that's been really exciting for me. So we're going to get to the mysteries now. From all the work I've seen and done in astronomy, I think we can really condense two things as the most exciting mysteries, and this is my opinion. One is a really big one, and it is, what does our future hold? So we're looking ahead tonight. What does our future hold, both for planet Earth, for our galaxy, and for the whole universe? And that's such a vast question, there are many, many books written about it. But I want to kind of touch on some of those subjects and how we study those things. And the second question, I think, is really important to us as living things. Are we alone? There are literally trillions of living things on planet Earth, from the smallest, plankton and bacteria and viruses to the largest structures, forests, woolly mammoths that used to live here, gigantic creatures, and everything in between. And we consider ourselves, maybe arrogantly, the most intelligent of those. We built technologies, but as we know, our technologies may destroy the habitat that we rely on. So what does intelligence mean? What does life mean? And what's the chance of life elsewhere in the universe? I think that's a really exciting one. So we're going to start with our future. Are you ready? Okay. So we've talked about stars a little bit. I've studied stars for about 15 years professionally. And as I said, they start in a nebula, a cloud. All stars begin their life in a nebula. And then what happens next in a star's life depends very much on how big it was when it was born. So most stars are sun-like stars. So they're about the same size as the sun. Some are a little bit bigger, some a little bit smaller. But basically, they're pretty steady for billions of years. They evolve into red giants and planetary nebulae and white dwarfs, and then the gas goes back into space and forms another nebula. So it's a circle of life, it's just like the Lion King. If a star is really unusually big when it's born, so it just happens, random processes, a piece of gas that's a bit bigger than usual forms a clump and then forms a star, then we get a massive star. That's actually the physical, technical term for it, a massive star, more than 8 times as big as our sun. And then it has a very different life. So they're kind of like the celebrities or the billionaires of stars. There aren't many of them, but they're kind of big and annoying and have an oversized effect on everything else. So a massive star burns really fast, shines really brightly, uses up more resources than everyone else. It turns quickly into a red supergiant, so this vast, bloated star. And then it explodes as a supernova, and that disrupts a huge area of space around it. And then it turns into either a black hole or a neutron star, which we'll maybe discuss a little bit later. So it's really interesting to see how the way in which you're born, the way you are, how many resources you have when you're born really affects your life, which is a little bit the same as humans. So studying all these stars tells us what a life cycle looks like for any type of star. So a type of star like our sun has this kind of life cycle. And we've seen it millions of times. So we can actually see stars in different parts of that life cycle. And we can even, in some parts of the life cycle, see it change very rapidly. Like this part or this part. These things happen very, very quickly over even weeks or years. You can see the changes in a star. So we know this stuff pretty well. So what's the future look like for us in particular? Well, there's two ways to think about the future of our Earth. One is astronomically. So we know that the sun has been burning for about 4.6 billion years. Okay, so our sun is 4.5 billion years old. The Earth formed when the sun did, so it's pretty much the same age. And our sun burns hydrogen into helium. That's how it shines. So in the middle of the sun, most of the sun's made of hydrogen gas. It's the lightest gas there is. Those little particles in the gas atoms, they crash together and they break up and they release energy. It's quite a complicated process, but that's the basic way that the sun shines. Now, the sun shines steadily for billions of years, and then suddenly there's not enough hydrogen left in the middle where it burns. And it's kind of like when you're on the motorway and you realize you forgot to refuel and you've run out of petrol or your electric vehicle's gone flat. So when you run out of fuel, you grind to a halt. So if you're a star, you stop shining. And what happens when you stop shining as a star? Can anyone guess? Yeah. Yeah, very good. So it will shrink. Why will it shrink? What's making it shrink?
It doesn't have enough energy to sustain its size, so the pressure pushing in on its core.
Perfect. Yeah, excellent. So the pressure outwards caused by shining, so when the star is shining, all the heat and pressure is pushing outwards in every direction, and this balances gravity perfectly. So when a star's in a steady state, it just sits there quite happily. And when it stops burning, gravity wins, because the shining pushing outwards stops. So the inward force wins. So that was a great explanation, thank you. So when that happens with our sun, it will crunch down in the middle. That will cause it to heat up again, and it will start burning gas around the core. And this is quite an unstable process. It will make the star puff up. So our sun will puff up and become a red giant star. That is not good, because a red giant star is wider than the orbit of Mars. Now, where are we? So we'll be inside the sun. So that doesn't sound good. So this artist's impression, not a real photo, by the way, is our Earth when it's going to be absolutely frazzled. So imagine that. So as the sun gradually gets into becoming a red giant, or it increases its luminosity, which is the amount of power output year on year, then even before it becomes a red giant, we're going to be stuffed, because in billions of years' time, the Earth will become too hot to live. Now that is entirely unrelated to something that's happening on a much shorter timescale, which is a separate thing, which is us stuffing up the atmosphere. So that one we've got to sort out, but I won't do a lecture on that one tonight. Climate change. But hopefully someone else will. So the future of the Earth depends very much on the sun. So when the sun has run out of most of its fuel, shrink down, as you said, expand again, become a red giant star, and then it sort of finishes burning some bits and bobs around the edge, but then it just goes, I can't do this anymore. It starts blowing away its gas into space. Now this is a real image. I like to tell people when it's real or simulated. Most of these are real. This is a real image of what's called a planetary nebula. So there's a nebula, a type of cloud of gas in space, and in the middle is the cold, it's still hot, but colder remnants of the star that it's left behind. So this is a star just like the sun. It's become a red giant, it's puffed up even more and blown its outer gas into space. So this is what our sun will be one day. This is literally our future. And the Earth would be somewhere in here. Yikes. So don't hang around for that one. It's not as bad as you think, because this gas is very, very light. It's not dense at all. But unfortunately, the radiation from the star will be zapping our atmosphere and our oceans, so that's not good. So all of that will happen on a sort of timescale of about 5 or 6 billion years, so 1,000 million years. So we don't need to worry about it today, and certainly climate change is a more important question. But it's just interesting, isn't it, to know what's in store for us. And that our star isn't going to explode. That's good, because that's a pretty dramatic thing. It's like a nuclear bomb, but much bigger. So now we know the future of Earth, stuffed. The future of the sun, also stuffed. What is the future of the universe, and how do we find out? And I love this question. How would you go about finding out what the future of the universe would be? I mean, that's absolutely huge. The universe is a word that means everything, everywhere. It's everything that exists everywhere. There's nothing outside of it. It's all of space and time. It's all the energy, matter, particles, everything that you can imagine, and even time, which is kind of a metaphysical concept, but it really works as part of space as well. So, amazingly, we actually have hugely strong evidence that we know how the universe began, and that is the Big Bang Theory. I love this because you can test it 5 different ways, the Big Bang Theory, and they are completely different bits of evidence from completely different measurements. Either the chemicals, the ratio of different chemicals in the universe, whether it's the movement of galaxies in the universe, flying apart from one another, or a number of different things. We can actually take a picture of the fluctuations of energy that happened about 13 billion years ago. We can do all of these things. They're completely separate measurements, and we actually find that all of those things agree. There was a Big Bang about 13.8-ish billion years ago. We don't know why it happened. We don't know how it happened, but we know that today everything is expanding. And we know in the past everything was expanding because we can see back in time using really powerful telescopes. So when people first started using physics and science to figure out how to measure motions in space, they found out you could look back in time. Because if you look at a galaxy that's 2 million light years away, like our nearest galaxy, you can see that the light travels to us, that takes 2 million years. So the light you're seeing is from 2 million years ago. You're seeing what the galaxy was like 2 million years ago. So when you look at a galaxy 1 billion light years away, you're looking back in time 1 billion years. So you literally are looking back in time when you look out into space. And that's incredible. It's actually even a problem for when we send astronauts to Mars in the future or other planets, because the signals, Capcom, the chat between ground and the planet will actually take hours and hours. So they won't be able to just say, mission control Houston and chat back. That signal would take hours as a round trip. So space is big, is what I'm saying. But we can measure a lot of this stuff between now and the Big Bang. And this is just a photo, really, in our imaginations of that whole history of the universe. And every measurement we make of these literally trillions of galaxies, every time we do another survey with a big telescope, and you think, what are we doing? Why are we looking at millions of galaxies? Well, this gives us literally a whole picture of the entire history of our universe, where we came from. And it actually allows us to study fundamental scientific concepts that we then use here on Earth. And not for just making stupid stuff, like cat videos on YouTube. The uses of our technologies are so vast. I talked yesterday to a group in Hobart, about the tiny fundamental particles and why we study them, why we smash atoms together. And you think that's not useful, surely. But actually it helps us to make medical scanners that can find in high resolution where you have a tumor inside your body in a place that otherwise you would have to have a very dangerous, invasive operation. And we can then treat diseases as well using scanning that is non-invasive, because we can get radioactive materials and put them inside our veins and see inside of us. So all of this stuff leads to useful knowledge, and it's not just interesting and fascinating, which I find it, but it's really useful for everyone in our society as well. So that's what I love about this stuff. So there's a history of our universe on a slide, and really it was discovered because years ago, in the 1930s, around then, people were messing around with telescopes. They were measuring galaxies. They didn't know what they were at the time. They thought they were actually clouds of gas. They didn't know they were actually island universes, they called them. They didn't know they were just a bunch of stars that were sitting all together very, very far away. And that's what they are. They discovered that these galaxies were moving away from us, because you can use chemicals and the light they emit and the colors of the light that these chemicals emit, and you can see that the light has been stretched because the universe is expanding. So you can actually measure that quite easily. But we thought, well, the universe is expanding, but gravity pulls everything together. So maybe those two things would be, gravity would be maybe slowing down the expansion. So that was pretty much assumed that that would be what was happening. So one idea of the future of the universe is that, well, now the universe is expanding, but of course gravity would stop that because everything's pulling together, right? So there would be a balance. So the big theory was that there was a big bang, and come expand, expand, expand to the present day, and then it would start to crunch down again. So today we see the stars and galaxies in the sky, and in a few billion years, the idea is that they would all crunch together, get closer and closer, and we'd have all these galaxies barreling down on us, and then in tens of billions of years, the whole universe would squish down into a tiny point again, just like the opposite of the Big Bang. And that was called the Big Crunch. So that's one of the three ways we think the universe might end. But as we'll see in a minute, there's not really much evidence that that will happen. But you never know. Things change in science. So that's theory number one of our future of the universe. Now the second one is called the Big Freeze. Now this one is based on the fact that the universe is expanding and expanding and expanding. And not too long ago, about 15 years ago, a bunch of astronomers discovered that it's actually expanding faster and faster and faster. Now that discovery won the Nobel Prize, and you might have heard of an Australian-based astronomer called Brian Schmidt, who won the Nobel Prize for that discovery, as well as other colleagues. So some of that work was done here in Australia. Now, because the universe is getting bigger and bigger and bigger every day, and that is getting faster and faster, that's accelerating, astronomers were saying, well, why is this happening? What's pushing it apart? What is this magical push? Is it some sort of anti-gravity? What is it? What's this force? And we don't know. We still don't know what it is. But we give it a name so we sound smart. So we call it dark energy. Okay? So dark energy, we don't know what it is, but it's the force or effect that is pushing the universe faster and faster and faster. So if it keeps going like this, if the universe keeps expanding in the future, in 10 with 14 zeros after it years, so 10 with 12 zeros is a trillion, so that's 100 trillion years, there will be no stars forming anymore because everything will be so far apart. Imagine the crunching through gravity of stars forming. That will be superseded by the expansion of the universe. So no more stars can form. The last stars will become planetary nebulae, and white dwarfs, the little stars that are left over, the size of a small town, very dense cores, and they will die. So there will be no more stars after about 100 trillion years. That's sad. Then, quite quickly afterwards, another little while, there's no stars, so planets will just kind of fly off. Because currently planets are just tied to stars by gravity, aren't they? So there'll just be planets sort of flying off, and apologies for the Canva AI-generated planets. I don't know why that happened. After a little while more, the protons, tiny particles inside atoms, may well even get blasted apart as well. So even the very tiniest things in our universe will actually, because the universe is stretching so much, could actually decay or spread apart. So there are no more atoms, no more particles, no more stars, no more planets. Everything is dissolved and it's just energy. That is rubbish. Then there'll be black holes still, which are hugely compact objects. If they haven't already dissolved through this process, they'll evaporate. That will probably take this number of years, so 10 with 67 zeros after it. That's a huge number. So we're talking trillions of trillions of trillions of trillions of trillions of trillions of years. But in the end, because of the way that our outside black holes, the area outside is really unusual and it emits radiation, and that can actually shrink the black hole through a process called Hawking radiation that Stephen Hawking discovered. And as the universe expands more and more and more, in the end, there will be a process called heat death. And it will actually, it means the death of heat. There's no more heat, there's no more. Energy is spread out so thinly, it's like a cordial where you've poured a whole ocean of water into it. You can't taste it anymore. So there's no ability for objects to touch each other, interact with each other. It's really, really just dead. So that's fun, isn't it? Which do you prefer, right? This one or that one? Who goes with a crunch? Hands up. Crunch, okay. Heat death, big freeze. Okay, neither. Quite a lot of people for neither. Okay, all right. Well, it gets worse. There's one more. Okay, now this one. So honestly, current science says this one's the likely one. This is what we're headed for. So the universe gets bigger and bigger, colder, cordial, pour an ocean in. Oh dear, we're all dead. So that one probably will happen. But we don't know for sure. The other theory, okay, when we study this dark energy, this pushing that pushes the universe bigger and bigger and bigger and makes it go faster and faster, as I say, we don't know what that is. But we want to know, was that different in the past to now? Was it expanding faster and faster in the past? Or was it getting slower in the past? So we look at galaxies really super far away, 10 billion light years away, using really powerful new telescopes. And that helps us to try and measure whether dark energy is changing. And I'm not one of the researchers who looks at dark energy, but there's very smart people doing this research right now. And they are finding hints that dark energy may have been different in the past. So that means it could be different in the future. The universe might go different pushes, different pulls, different motions of this expansion. So what if it gets faster? Oh my goodness. This is going to be terrible. So what we'd have is the Big Bang, universe gets bigger, you are here, so this is us. And if it keeps getting faster and faster and faster at a heavier rate, about 22 billion years from now, which is a lot sooner than the previous one, the entirety of space could rip and actually just pull apart. All the atoms dissolve, the Earth explodes. It will be really, really quick. So it's really about whether the universe expands into terrible, deathly oblivion slowly or a bit faster. So now we've got three options, okay? So we're going to have the big crunch where we all smash together again. We're going to have the middle one, the big freeze, or we're going to have the big rip. Who wants the rip? Oh, we've got some RIP fans now. I like that. That's good. Maybe a quick death. Maybe that's nice. You know, it's like a, oh, bye then. And then this one is like a depressing kind of demise type of one. Who likes that one? Good. Okay. No, that's good. That's good. It's like psychology, this. And then who likes the bang, the crunchy one? Yeah, I like crunch. Interesting. Because I think we like, as humans, the idea that we return to where we came from. I think that's comforting. I think that's probably the origin of religions and things like that and belief systems throughout time. So I can understand. But cosmologically, we have to try and look at the evidence. But we don't know which one is true. Crunch, freeze, or rip. I love these. No, they're all big. Yeah. The question was, do you not have any endings without big? But no. I guess it could be the little crunch. Because it is quite little, isn't it? That's great. So what we're doing to find all this out, people are doing surveys of dark energy. So they're looking at exploding stars really, really far away to try and measure how fast the universe was expanding in the past. And they measure that and see if it's changed, how much it's changed. Is it accelerating faster and then slower, or is it really constant? And that helps us understand which of those three will be our ending. They look at the growth of galaxy clusters over time, so seeing how galaxies formed and how they grouped together to measure the fight between gravity and this dark energy stuff. They look at sound waves from the early universe, which is amazing. This background picture here, these blue structures, is from a real scientific measurement. They're called baryon acoustic oscillations, and it's basically like a sound wave of the Big Bang. Imagine the Big Bang kind of going rah, bomb and reverberating through the universe. That actually created places in the universe, structures, where more galaxies formed than other places where there are fewer galaxies. So you kind of get this big shape in space that tells you about how much energy is in this stuff. It's very complicated. I don't fully understand it. Don't ask me questions. Okay. The other one is looking at gravitational lensing. This is cool too. So you know how in a telescope or a pair of glasses, the glass is bent and it's a lens, so it moves the light. So it sort of bends the light. You can see better, or you can see further. In space, gravity from objects like galaxies actually bends light, like a lens. It's amazing. So gravity bends light around it. That's what Einstein discovered, one of his very good discoveries. So this is really important. It helps us to understand and see really far away objects, measure where huge clusters of galaxies are, and to do all this kind of stuff. So there's heaps of really interesting ways, and we never make a conclusion from one piece of evidence. We always try and look at lots of different ways to measure it, because as scientists we like to test really thoroughly. We don't just announce something like, hey, we found a thing, and then we look stupid when it wasn't true. So we test for years and years, and that's why it's a bit tedious, waiting for new results, but definitely worth it, because you know there's been a rigorous process behind it. So, what's the scariest part of that? Are you scared? Or do you think, that's okay? It's a long time away. The more important thing is we look after ourselves right now. This stuff is billions of years away. So the second question, I love this one. And it's not something I study overtly, but I wrote a book about it for children, and I find it really fascinating. And I've got colleagues who work on this problem. Is, are we alone? And I promise I've only got one slide of a really boring dead man, but this guy lived, Epicurus lived more than 2,000 years ago. And I was trying to figure out who the first person was to think there might be life elsewhere in the universe aside from Earth. And he made quite a rambling quote, but what it was essentially was questioning whether or not living things could live elsewhere. And that's just such a fundamental question. I'm sure there's loads of other civilizations who didn't write things down, who have also asked the same questions. It's just that we happen to find bits of paper from this chap. So the first people to look through telescopes and say, is there life elsewhere? Giovanni Schiaparelli was an Italian astronomer. He had a big telescope, and he used to look at Mars, and he was obsessed with Mars. He actually drew a lot of pictures of its surface. So a lot of these astronomers back in the 1800s, they would sit for hours and hours and draw pictures. And he thought he could see this really interesting structure on the surface of Mars. He would draw all these maps. He would say, this is mare, that means sea. And he's got these rivers and channels as well. And he's named all these little places like Eden and Hellas and things. So he's got quite a self-important kind of approach to it. But interestingly, he kind of came up with this first idea that Mars has rivers and lakes. So he's actually named these, even though all he was seeing was sort of dark and light patches. So he's really convinced himself in the 1800s that there were actually maybe the conditions on Mars where there could be life. Now this guy really took it and ran with it. Percival Lowell, he was the discoverer of Pluto, which is not a planet. But he got this finding of Giovanni Schiaparelli that there were these canals on Mars. And he got a telescope and he had a good look. And he said, yeah, I can see them too. And he actually drew really intricate pictures, but he didn't just do that, he got obsessed with it. He drew hundreds of images and maps and gave them names. And he said there were actually ice caps as well on Mars, which is true. And he said these aliens actually live on Mars, and they use these artificial channels, like canals, to transport water from here to here where they live. So he's actually created this whole world, and he was going absolutely gangbusters, talking about it and writing books about it and all sorts. Ka-ching! When we actually sent spacecraft to look at Mars, to fly past, to take high resolution images, there's no canals on Mars. They just made it up. So we think this guy genuinely had cataracts. And then this guy was just an opportunist. So he was a real astronomer, but often you find that there are a few astronomers who like to tell tall tales in order to, make a name for themselves. And this appears to be one of those situations. Anyway, Mars doesn't have canals. It does, though, have dry riverbeds. They're not in the places that he drew, but there are polar ice caps made of carbon dioxide mostly. There are dry riverbeds, there are mountains, there's a giant volcano called Olympus Mons. And it's a really interesting place. But none of these features are actually telling us that there's life there. And we know that because we haven't just taken photographs, we've actually sent a bunch of spacecraft. So we sent spacecraft through the atmosphere of Mars. So Mars actually has an atmosphere, it's quite thin. And its surface basically looks like Western Australia or parts of inland Australia. It's quite iron-rich, and it has permafrost underneath it in parts. There seems to have been riverbeds in the past. So it looks like, a good place where you think, well, maybe there was life here previously. So we go and we grab rocks and we zap them with lasers and see what comes out, see what gases are in there, see what the rocks are made of, and we look really carefully with microscopes to see if there are any fossilized forms of life. And so far, after looking for a very long time, we've found nothing. We've even sent a helicopter there. This is a real image of the Ingenuity helicopter that went up to Mars about a few years ago. And you can see the tire tracks of the rover there. And it deployed a helicopter. It's kind of like a drone, and it flies around Mars. It's got quite big, what do you call them? Finny things. What are they called? Rotors. Because there's a thin atmosphere there. So in future missions, we're going to be able to actually discover a bigger radius and actually look further afield. For example, this mission is going to be launched pretty soon. I think I've got a little video here I can click. But this is a planned mission to Titan. So we're not just going to look at Mars, but other bodies. Titan's Saturn's moon, biggest moon, and it has an atmosphere as well. So we're actually going to send a kind of a drone or helicopter to the moons of other planets too. So that's a kind of exciting way to explore them. And really for these kind of missions, you don't need human beings too much. So we do send spacecraft all around the solar system. We sent them to all the planets. We know quite a lot about these planets. We haven't been everywhere, but we see no signs of life in our solar system. So when I was a kid, there were just the 9 planets in our solar system, and then we killed one, Pluto. I was actually at that meeting where they killed it. I was in the room, and everyone was very gleeful. There was about 1,000 astronomers in the room where they voted to demote Pluto from being a planet. But it doesn't really matter because it's still a minor planet or a dwarf planet. And as we know now, there are literally probably trillions of planets in our universe, because when we look using telescopes at other stars, we see them. We've discovered more than 6,500 so far. So there's 2 main ways we look at stars and discover planets around them. One is the wobble method. So we look at the star and we watch it wobble slightly. We can't see the planet because it's too faint, but we just measure it wobbling. Why would it wobble if it has a planet? You think? Anyone? Yep. Excellent. The planet has a gravitational pull on the star. So they both exert a gravitational pull on each other. And the fact that there's a planet there makes the star wobble ever so slightly. And it does it in a regular way. So it wobbles that way, that way, that way, at a very regular cadence. So we can actually infer, using physics, what the planet is like. And in some cases, there are more than one planet going around. The other way is if we're looking at a star, and again, the planets are too faint to see usually, but we happen to be side on, and the planet, as it orbits its star, goes in front, kind of like an eclipse. We can see the light of the star get dimmer while the planet's moving across. And it does this again regularly. We can tell the orbital parameters, like how long it takes to go around the star, how big it might be. We have to make a few assumptions, but we can discover planets in these ways. There's also a really powerful way that's going to be used with a new telescope called the Nancy Grace Roman Telescope, which is the new kind of, bit like the Hubble Space Telescope, but way better. So they're going to launch this, I think, in the next couple of weeks. And this will enable us, using gravitational lenses, which I mentioned earlier, to actually discover really small planets, because the current planets we find are usually quite big, like Jupiter and Saturn size or bigger. We're going to be able to find now Earth-like planets using this technique. It's a bit complicated, but basically you get gravity bending light, you get 2 stars, light, bending, but then you get a planet in the mix and it suddenly goes really bright because it bends it even more. So it's really a way of looking at light and inferring that a planet is there. Pretty fancy. And a cool thing you can do too is you can measure the atmosphere of the planet. So it's hugely far away, it's so tiny you can barely see it, but we can measure its atmosphere, again, if there's an eclipse. So here's the distant star, and here's a planet that's going across. If this planet has an atmosphere, with new telescopes we can actually measure the light coming through from the star, and little bits of light get nibbled out depending on which chemicals are in the atmosphere. So we can measure, is it like our atmosphere with nitrogen and oxygen and carbon dioxide and water vapor, or is it very different? So we can start to get an idea if there might be a lot of carbon dioxide, for example. Could there be plants on that planet? If there's a lot of oxygen, is it similar to our Earth's atmosphere? So we can start finding targets that are very Earth-like to look for alien life. We can also see new solar systems. This is a real image from a radio telescope in Chile called called ALMA. And here's a star, and it's inside a cloud of gas. The star is currently forming. It's pulling together, and there are these rings around it, and these are new planets forming out of these rings. So this is exactly how our solar system formed. This isn't an artist's impression, this is a real picture. You can tell because it's rubbish. That's how you tell. Real looks amazing. Real looks fuzzy and rubbish. AI looks amazing. So that's how you know. This one might actually be a photograph, but it's a real telescope. So in the future, this is the Square Kilometre Array telescope that I was talking about earlier. I spent 10 years working on this telescope, but many people have spent 30 years developing the ideas behind it, the engineering designs, raising all the money. It's a global project to build the world's biggest telescope, and this part is in Western Australia. The other part is in South Africa, and it looks like kind of weird television aerials that are on your roof, but basically it's a radio aerial without using the dish. When you look at low frequency radio waves, you don't need the dish. The ground does that for you. They put a sort of metal mesh on the ground, that's enough. So you don't need the dish. So basically it's using the Earth as a telescope. All these bits are spread out over kilometers and kilometers and kilometers. And you make it spread out so you can see really far away, really good detail. And what we're trying to do is measure really, really far away things. What you can also do when you're looking at those really far away things, you can see if you get any weird signals. And what we do is we chop the signals up and see if we see anything repeating, really bright, really unusual, or patterns in the sounds, the radio waves that we listen to. And in that way, some people look for signs of alien civilizations, because what you can do is look for patterns, and imagine you're trying to speak to an alien, you might use binary or something like that to try and get someone's attention. In fact, in 1974, we did the same. We sent this signal from a radio telescope in Puerto Rico. I've been to this telescope, it's fantastic. Unfortunately, it's broken now forever, but it was the world's biggest telescope for a long time. But in 1974, they'd just got some funding. They'd resurfaced the telescope and they were celebrating. So they got Carl Sagan, a famous science communicator back then, to do a big opening. And to get a splash and to get the media there, they decided to beam, unwisely perhaps, a signal into space. Usually you just listen, but in this case we're beaming out. So what they beamed out was this. It was a message to aliens. Headless. What this is, it actually describes a number of things. This is the numbers 1 to 10 in some code that I'm not sure I understand. These are the different chemicals that make up part of DNA that obviously tells us our chemistry and biological imprints, how to grow, how we reproduce, all that stuff. This is the DNA strands itself. This is supposed to be a person, they forgot the head. Really worried about that one. And we've got the solar system here, so we've got the Sun, Mercury, Venus, Earth. It's higher, as you can see, that's where we live. Mars, Jupiter, Saturn, Uranus, Neptune, and Pluto was there because it was 1974. And then this is a sort of representation of this dish. So here's the dish and the beaming radiation coming out. So this is a real signal that we beamed out towards a globular cluster that's 25,000 light years away. So this was beamed out in 1974, just over 50 years ago. It's got nowhere near this globular cluster, this cluster of stars. So we don't expect to hear back for another 50,000 years. So that's probably for the best, I'd say. And we certainly don't make a habit of beaming messages out. But interestingly, when we go back to these surveys, we have planets within 3 light years, just over 3 light years of us. There are planets around Proxima b, Proxima Centauri, the nearest star to us. So that's just over 3 light years away, so it takes the signal 3 years to get there. So if we sent that in that direction, they would have got it by now, been able to read it and send a message back. Each message would take 3 years to get across, but we'd still be able to chat with aliens, and I find that quite interesting. But anything further away, and really there's no hope of communicating, even theoretically, because the fastest speed of signals is the speed of light, and there's no way we know to break that. So unless there's magical portals through the universe, like wormholes, we will never probably speak to any aliens. I find that quite sad. Well, I'll just have to keep watching Star Trek. So this is just some beautiful illustrations from one of my children's books, Aliens and Other Worlds. But I think it illustrates nicely that, the life that we have here on Earth, it's so diverse, it's so incredible. We think of life as, the obvious big things like us, the animals, the fish, the birds. But there is so much life just on our skin, the amazing flora and bacteria and all the tiny little bits and bobs that live within our body. And even in extreme environments across planet Earth and in extreme conditions, in volcanoes, the bottom of the ocean, at the top of mountains in Antarctica, there's life flourishing. So it really is incredible. So if we think about aliens, what they would look like, we can't just think little green men. We have to think more creatively than that. What would they look like? Maybe some funny looking nuclear dolphins or whales. But on Earth there's 170,000 species of mushroom. They might look like mushrooms. There might not be any animals out there. There might just be a beautiful forested planet. Can you imagine how beautiful that would be? Or there just might be an ocean teeming with life and krill and yabbies and who knows. There just might be anything you can possibly imagine. And I love to think about that. And even if we don't find life out there through any of these methods, even if it's there, we can still imagine it and hopefully get some inspiration. So I hope you've enjoyed those two very different parts, which is our future of our Earth, a depressing future of the universe, whether it's being crushed together like a car at the crushers, or whether it's expanding forever or twanging like a breaking piece of elastic, to maybe a more uplifting feeling of thinking about life elsewhere. It's been terrific talking to you. Thank you so much. And I'm really excited for the Q&A. And certainly afterwards, I'll be doing a book signing as well. So please come up, say hi, chat to me, especially young people who might be interested in doing science in the future. Thank you very much. Thank you. I'll put this one up.
On the test, which is sitting on a stool on a stage.
Yeah, this is always dangerous. Wish me luck.
So now we're in this special part of this evening where you do get to ask your questions of Lisa, and we have people coming around in the audience, so please put your hands up. Please wait until they arrive with the microphone so that we can all hear your questions. And I have a question for you, but before I do, I was thinking about in your slides about these three possibilities, and I was thinking about your explanation of all of the zeros that are between now and then. And I was thinking, what are the chances that we are right about one of them?
Yeah, well, it has to be one of them. There's only three. You'd think there were two, really, getting smaller or getting bigger, but it's like how fast do you get bigger? So there's really two options. Actually, for many, many years, everyone really thought the universe was steady. It was a steady state theory. And that was just assumed knowledge until we started measuring movement. So, pretty much all of human civilization, no one's really questioned whether or not the universe as a concept even exists. But it's really since the Greeks and all the civilizations before who thought about planets, for example, a lot assumed that the Earth was center of the universe, and that was quite a popular religious idea, and that then there were the planets rotating around us, and then the fixed stars, but no one really considered galaxies or anything bigger because they couldn't see them with the naked eye. So it was when we discovered technology that enabled us to see beyond there. Now we know all of that stuff is just our absolute neighborhood. There's so much more out there. And that's a similar thing to any other field of study where, in the past we couldn't study the oceans because we couldn't get submarines down there, or we couldn't, study remote areas. It just goes to show what technology can do for us.
It's a wonderful example of all of the different areas of endeavour that have to come together to give you that new information to think new things.
That's it, yeah.
Do we have a question from the audience? There's one down here on the front. And
Fab, my little mate, yep.
There's a microphone coming to you.
Okay, here it is. It's going to run down.
Is a white dwarf star, after it dies, is that the core of the star, or would it be like just a little bit of excess around the core?
Yeah, good question. So the core of a star isn't well defined. It's sort of the middle bit. It's generally considered what's undergoing nuclear fusion, right? What's burning. So that's the core of the star when it's burning. And then, as you say, your star evolves or the gas pushes off, the middle stays there. But normally then that middle part shrinks because it's not really burning. I think I've lost my mic. Thank you. So what's happening is the middle bit's not burning anymore, and it collapses down into such a tiny point that the material stops being normal particles. Those particles crush together really, 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 really tightly, and that is so dense that it weighs the same. A teaspoon of that material weighs the same as an elephant, right? So it's massively dense. It's almost as dense as gluten-free bread, right? So it's that bad. So I think that's, so that's a white dwarf. So the really dense material. It's called degenerate matter. And then after that, it kind of, the white dwarf stays the same, but it's just kind of glowing with its leftover heat, really. And that just glows and glows for billions of years and eventually kind of goes and kind of, it sort of stays there, but then it stops glowing and it sits there, a dead core. It's going to take tens of billions of years. I think we've lost me again. We've lost me again.
What's your favourite part about learning about the universe?
Cool. Wave your hands so I can't see where you are. Oh, there you are. Hello. Thanks for that question. Oh, goodness me. My favourite part, I love the fact that sometimes you can, in life, when you go and walk on the beach and you see an amazing sunset or something like that. It would be a sunrise here, right? You see an amazing sunrise. And that is, you're the only person in the world to be seeing that exact vision, right? That angle from the same place, the same foreground, the same sunset, the same clouds. So I love that. So as a scientist, it's the same kind of thing. You think, well, I'm looking at this star. Nobody's ever seen this star before. Or I'm looking inside a cloud of gas using a radio telescope. Nobody's seen inside there before. So you feel very special and honored, but also you're very privileged to use very expensive equipment that not many people get to play with, those amazing telescopes, and going to somewhere like the Parkes radio telescope and actually using that. It was in the film The Dish. Everyone loves that film. And having actually been there and worked there, it's just incredible. It's a privilege. And I get to work with people from all around the world, and I get to travel to different interesting places as well. So there's so much interesting about working in science and technology, and obviously you get that in other disciplines as well, but that's something I really love.
What would aliens react if they saw the comets that we send to Mars?
Ooh, what would aliens... So I think they would think our spacecraft were very rubbish. What do you think? Because they're quite rubbish, aren't they? They're little boxes. Most spacecraft that we send to Mars are really the size of a normal car. So like your Kia or something, whatever you've got. Like there's just a box, and then they drop a rover. They might be a bit bigger, like some of the size of a van or something, but you know, they're quite small, they're quite basic, they're made of metal, they're a bit ugly. We're not very good at this yet. We've only been doing it for, 70 odd years. So, if our civilization continues, for hundreds more years, I think our spacecraft will look way more cool. And maybe we should wait and not talk to aliens till we've got cooler stuff. What do you think? Yeah, thank you. Thanks.
Thank you. Now we can both have one. Next question. Over. There's one down the front here. Was there one up there, Taryn? Yep.
Up here, Juanita, yeah. We got time.
Where would we go if we had the technology to escape from the sun exploding?
Ooh, wow. Well, I'd love to hear your ideas about that, but my ideas, the trouble is, even if we could go in a spaceship at the speed of light, which is the fastest speed there is, it would take 3.3 years to get to the nearest other place. So where there's another star and another planet. Now that planet's not very good because it doesn't have an atmosphere, probably, and it's around a really rubbish star. It's not like our star, but it's too cold and doesn't have a nice sort of environment. So the problem with escaping is there's nowhere that suits us that we can find. And that is a lesson, really, that we have grown, our life forms on this planet have grown over millions of years to be perfectly balanced with the environment. So that's really important for us. So if we went to another place, we couldn't breathe there, we couldn't live there without living underground or in a dome or something. So we've got to kind of hope that our planet is the place we want to live. Elon Musk can go there, that's fine.
So I'd say my question is probably highly controversial and definitely theoretical.
Excellent.
So we were discussing particle expansion in space. So as particles move further apart, could the reduction of resistance cause an increase in the speed of the expansion of the universe over a large enough distance? Like we know the law states that objects continue to move until an opposing force acts upon it. Mm-hmm. But what if our data set for a vacuum just isn't large enough to disprove that?
So go through the first bit. So if the particles move apart, then explain the first bit to me.
So as they move further apart, there's less resistance. They stop acting on each other because they're so far apart.
You mean gravitationally or through?
Through interaction, through gravitation, really in any way.
Yeah.
So could the reduction of resistance cause an increase in speed?
So they've taken all of that into account, so that all of those models would be talking about all of that. The major mass in our universe is not particles like that, but it's actually dark matter as well. So there's kind of the most of our universe is stuff we don't even know if it's made of the particles that we understand. So that's going to be a much bigger component of this. So as best we can, theoretical physicists have made models like that. It's very hard to do, but it's not really about that. It's more about this dark energy stuff is expanding the space between things, not the things themselves. So it's kind of, there's kind of two ways of looking at it, but what we're finding is that the acceleration of the universe is far stronger in that sense than any gravitational or other forces. Other forces only act on very small distances. Gravity gets weaker as you get further apart by a lot, so that doesn't really help you either to keep the universe together. So there's nothing, even with dark matter, that can keep the universe together in the way that we want to. We want to, because we love the stuff being together, because it means we can talk to each other.
We have a question at the front. Was there another one up the back as well?
Yeah, we've got one up the back.
Cool.
Yes, Professor. I remember in 1965 I was studying physics at Newcastle Uni, and the professor said, "Great news, the universe is expanding," and when the steady state was the way. So things have certainly developed.
Yeah.
Do you think, when you said we're not likely to find out whether there's life on another planet, we don't know what dark energy is? Epicurus said there are, could be infinity of universes. Before the Big Bang, even before the Big Bang, was there anything? Where did the Big Bang, what caused the Big Bang? Are we ever going to get any answer to these questions?
I have no idea, honestly. But do you know what? We've come so far, and we're now talking about questions that we couldn't even really conceive of before, because you make these leaps. So one of the leaps was what we were just talking about, where you thought the whole universe was just what you can see with your eyes, and then you discover there's other stuff out there, and you discover a whole new field, whole new questions to ask. So I think through the history of science, we will have more of those leaps. How close we'll ever get to understanding, for example, what was before the Big Bang, I don't think we'll ever be able to, or if there are multiverses, more universes parallel to our own, or, we probably won't know that, because there might not be any physical way in which we can gather data for that. And that's cool, because we can just imagine it and do sci-fi. But there are lots of things we will be able to measure, and those big leaps and bounds through history really give me hope that there are very, very cool things out there to discover, and they might not be the things you mentioned, because they're just theories that we come up with right now. I'm more interested in the things we can't even imagine right now, and I think they will be the most exciting. It's very, very, very cool, though, all of it. Hi there. We're at the back first.
You might have answered it, but... Oh, sorry.
No, go ahead, please. I'm just saying this. Something else.
You might have answered it just then, but I was going to ask, was the Big Bang of 13.7, 13.8 billion years ago the first one, the only one? What's the dominant thinking about notions of multiverses and infinity in the real sense?
Yeah, there are no physical pieces of evidence or ways to measure that as yet that we know of. So anyone claiming that will be trying to sell you a book. So you'll find that. People will, I think it's interesting and important for people to ask these questions, but they all live in kind of theoretical physicists' notebooks right now. And I'm a more observationally inclined astronomer, and I think that stuff is important, and observation is important, but the two sometimes don't meet. So that's the difficulty and that's the challenge of it. Sorry if that's a boring answer, but we don't know.
I think we have time for one more, and I think we have another.
Great.
Yeah.
What do we think the boundary and shape of the universe might be a bit like?
Yeah, we don't know, but this will, again, possibly be helped by understanding whether dark energy is changing over time or changing in position in the universe. You imagine, it's hard to even imagine accurately the universe's boundary or shape, but essentially it already has a growing size, we know that. We know that space itself is expanding faster than the speed of light. So then there's a boundary that we can ever see or touch, and then there's a boundary beyond that. And a lot of theorists consider that to be in some way infinite, because it's growing and you can't see beyond. So there's a lot of kind of debate, and the mathematics is sometimes more instructive than trying to imagine it yourself. We make mistakes when we try and imagine and explain things. That's why it's difficult to sometimes explain these concepts, because none of us really understand them, or we don't have an easy picture for us to all go, oh, that's how it works, because we don't know how it works. All we know is what we can measure. So, imagine a balloon animal and you've twisted it and it goes bigger in this part and smaller in that part. Is that possible? We don't know. Again, is dark energy uniform is the question. And what does that say about the shape, boundaries, directions of the universe? It's hard to ever know because we physically can never see beyond that boundary. So again, another place we can't go. Exclusive club. Thanks for the questions.
So yes.
Star Trek for me. I never got into Star Wars. I've only seen one of the films, and it was that awful Jabba the Hutt thing, and I hated it so much. I never watched the other ones.
I love that you snuck in an extra question there. Well done. Thank you for these fantastic questions. Please join me in giving Lisa another round of applause. I want to give our thanks to all of you in the room, but also those that have joined online this evening for really helping this become a wonderful sharing experience of both curiosity and knowledge. And by coming along, you really have helped our conversation to kick off National Science Week. So thank you. I hope you enjoyed the discussion as much as I did, and I hope you heard in what I heard today, Lisa, both the incredible knowledge that you shared with us about what we know, but just how many times you've said we don't know yet. And I think that's an amazing invitation to those in the room that really want to either be part of building the technology that changes what we can know, or putting that information together for the next talk when you come back next
absolutely.
time. Yeah, wonderful. So I have gone too many pages. I've really enjoyed hosting tonight, and we really love hosting this series. They're a way for us to share thought leadership on many topics and the amazing work of people in our country, beyond, and right here from the University of Newcastle as well. Today's our first event for National Science Week, and there are a lot of exciting events this week, so please join us for more of those and keep a lookout for what's on. And on the 24th of October, we'll be back here in the Conservatorium, again in partnership with TEDx Newey. So stay tuned for more information about that, and it should be another great event. So that brings us to the end of the formalities of tonight. For those in the room, please do join Lisa and myself in the foyer for some more conversation, something to drink, something to eat. And thank you all very much, and have a wonderful evening.